So friends, welcome back to Hydrogen, and this is your Cloud Mentor Gaurish again, and we are talking about the hydrogen peroxide now. Hydrogen peroxide, otherwise H2O2, was discovered by the French chemist L.J. Thénard in I think 1818 by the action of sulfuric acid on barium peroxide. Initially, it was named oxygenated water. It occurs in traces in air, rain, snow, some natural waters, and juices of certain plants. So here we need to study general methods of preparation. General methods of preparation. Okay, general methods of preparation. So the first method is by the action of the dilute HCl on anhydrous barium dioxide by the action of HCl on anhydrous barium dioxide. Okay, and Thenard, a French scientist, who was the one who prepared H2O2 accidentally in 1818 by the action of dilute HCl on barium peroxide, while he was trying to evolve some new methods for the preparation of water. He called it as oxygenated water, and that is the water with more oxygen, right? H2O is the normal water. When one oxygen is added, it becomes the hydrogen peroxide. So it was called as oxygenated water by him. And now the reaction is BaO2 reacts with hydrogen chloride, giving barium chloride and the required amount of H2O2 or the hydrogen peroxide. So this was the first preparation method, and the second one is by the action of dilute H2SO4 on Na2O2. Okay, with the action of dilute H2SO4, that is sulfuric acid, on anhydrous sodium peroxide, that is Na2O2. And while preparing H2O2 through dilute H2SO4 and Na2O2, the latter is added. The latter one it is added slowly to ice cold 20 percentage H2SO4. Okay, ice cold. It is the that is Na2O2. Sodium peroxide is added to 20% ice cold sulfuric acid, and on cooling crystals of Na2SO4, Na2SO4, H2SO4, Na2SO4, 10H2O. It is hydrogenated, or I mean aqueous, and separate out from H2O2. And these are filtered off while some impurity as Na2SO4 remains present in H2O2, and the reaction proceeds as like this: Na2O2 added with ice cold 20 percentage H2SO4. H2SO4, that is ice cold 20 percentage. Okay, percentage concentration, and it gives off the impurity Na2SO4 along with the our hydrogen peroxide, that is H2O. And this was the second method, and we have another one more method, that is by the action of dilute H3PO4 on hydrated BaO2 or the barium peroxide. Okay, okay, was it action of dilute phosphoric acid H3PO4 with hydrated barium peroxide. Okay, and a bit modified form of the above written process. This one, okay, or the mixed with the application of Thénard's reaction is used more commonly for the preparation of H2O2 or the hydrogen peroxide in laboratory. Here, hydrated BaO2 is used instead of anhydrous barium peroxide because BaSO4 barium sulfate formed as the byproduct of the reaction forms a layer on barium peroxide, thus preventing further reaction. But with hydrated barium peroxide, such a problem does not arise. And secondly, the H2SO4 used catalyzes the decomposition of hydrogen peroxide, and also hence comparatively weaker acids like phosphoric acid H3PO4 or H2CO3, etc., are used in the place of H2SO4. Okay, the reaction can be written like this: 3BaO2 reacts with weak acid like H3PO4, giving the precipitate Ba3PO4 twice with our hydrogen peroxide. And insoluble barium phosphate is filtered off. The filtrate consists of hydrogen peroxide. Filtrate consists of hydrogen peroxide, and the barium phosphate is decomposed by dilute sulfuric acid. The barium phosphate is this one is filtered off, and the filtrate consists of the reaction will be like this: Ba3PO4. Okay, is decomposed by H2SO4, giving 3BaSO4 plus 2H3PO4. Okay, BaSO4 is removed by filtration, and orthophosphoric acid is used again. This is orthophosphoric acid, and we got the orthophosphoric acid regenerated here for the use again. And the other process, the fourth one, it is the Merck's process. Merck's process. Okay, and H2O2 can be obtained by passing a current of carbon dioxide through a cold, pasty solution of barium peroxide in water. That is, reaction is barium peroxide passing carbon dioxide through a cold, pasty solution of barium peroxide in water. So that is passing CO2 with water. It is cold pasty solution of barium peroxide and giving barium carbonate and our required amount of hydrogen peroxide. The barium carbonate being insoluble is filtered off. And now these were the simple preparation methods, and now we need to know the industrial preparation methods also. And the industrial preparation methods. Industrial preparation. Industrial. So in industrial preparation, the first one, it is by the electrolysis of H2SO4 or NH4HSO4. NH4HSO4. By the electrolysis of sulfuric acid, or ammonium bisulfate, that is NH4 HSO4. At a high current density, at a high current density, high current density, and the electrolysis of 50% sulfuric acid is done at 0%, 0 degrees Celsius using platinum electrodes, and here per disulfuric acid is formed. It is per sulfuric acid, is H2S2O8. It is per sulfuric acid is formed by this reaction, formed at the anode. Okay, and the reaction is like this: H2SO4 is broken into H plus and HSO4. And HSO4 at cathode, the reaction will be, the reduction reaction will happen there. Okay, that is H plus ions will get the electrons or gain the electrons and becomes hydrogen gas, plus 2 electron giving 2H, that is giving H2, that is hydrogen gas. And at anode, that is oxidation. Anode, it is oxidation, and the reaction will be HSO4 minus releases electrons and forms H2S2O8, that is plus disulfuric acid, H2S2O8 plus 12. Okay, and thus this H2S2O8 on hydrolysis gives H2O2, which is separated by distillation and the reduced pressure. When NH4 twice SO4, or the ammonium sulfate and sulfuric acid are mixed in 1:1 ratio, the ammonium bisulfate is formed, which is electrolyzed to give ammonium persulfate, and by using platinum electrodes at 0 degrees Celsius, and that reaction is like this: 2NH4 HSO4 giving 2H plus 2NH4SO4 minus. Okay, and at cathode the same reduction occurs: 2H plus 2 electron giving 2H, and that's hydrogen gas is formed here. And at anode, this oxidation takes place, and 2NH4 SO4 minus giving NH4 twice S2O8 plus 2. The ammonia persulfate so formed is hydrolyzed by heating with water at low pressure, that is about 43 mm of Hg, resulting in H2O2. So in this two forms, that is by the electrolysis of H2SO4 or by the electrolysis of ammonium bisulfate, we can form the required amount of hydrogen peroxide industrially. And the second method is by the auto-oxidation of 2-alkyl anthraquinone. Okay, by the auto-oxidation of auto-oxidation. of 2 alkyl anthraquinone. 2 alkyl anthraquinone is oxidized as this is the 2 alkyl anthraquinone. So this is the 2 alkyl anthraquinone. Quinol, and this is oxidized by the reaction. First, it is reacted with the uh, catalyst is used. It's platinum with hydrogenated to get this product. To get the same one, but difference is here double bonds breaks and hydrogen gets attached here at O at the forming OH hydroxyl group here, and the reaction is like the same. OH gets attached here, here also OH gets attached. Okay, and this is how now 2 alkyl anthraquinone is formed. This is sorry, this is quinone. Okay, anthraquinone. This is quinone. This is ketonic group here. 2 ketonic group here. It is alcohol group. So this is 2 alkyl anthraquinone. I don't know. You can read that, but just hear me and try to write that or read that. And by the oxidation of this 2 alkyl quinone, it is by the air oxidation. Okay, air oxidation. It is reacted with the air, giving the final product the same 2 alkyl anthraquinone is got or regenerated the same by the oxidation of alcohol or the alcoholic groups. We get the ketonic group again. That is, we get 2 alkyl anthraquinone again. 2 alkyl anthraquinone again. Anthraquinone again, and we get the amount of hydrogen peroxide along with that. Okay, and the reaction is carried out in a mixture of organic solvents, for example, ester or hydrocarbon or octanol or methyl naphthalene, and the solvent must do dissolved quinol and quinol, and should resist the oxidation and be immiscible with the water. That's a condition for choosing the solvent. Okay, and now we got the hydrogen peroxide by different methods. Now, how to store this hydrogen peroxide? H2O2 gets easily decomposed in presence of metals, rough surfaces, sunlight, dust particles, glass, and alkali. Thus, it is stored in vessels of pure aluminum or in stone jars in dark. Concentrated solutions of hydrogen peroxide are stored these days in polythene bottles kept in refrigerators. Small amounts of stabilizers such as orthophosphoric acid, acetanilide, or sodium stannate are also added to the solution to be stored to prevent its decomposition. And what are the physical properties? So now we need to talk about the physical properties of H2O2. Okay, and the important ones are it is light blue in pure anhydrous form and odorless, syrupy liquid, produces blisters on skin and soluble in water, alcohol, and ether. The second point to note is that its boiling point is 152 degrees Celsius and freezing point is minus 0.89 degrees Celsius, and the further increase in boiling point of H2O2 in comparison with water is due to the reason that here intermolecular hydrogen bond is even more stronger than water, and the density of hydrogen peroxide at 0 degrees Celsius is 1.45 gram per cubic centimeter, and dielectric constant is 93.7. So the H2O2 molecule is diamagnetic polar and its dipole moment is 2.1 d. It has both polar and non-polar bonds as this HO H. Here between the bond between the oxygens are non-polar bond, non-polar, while the bonds between oxygen and hydrogen is a polar bond. Polar, polar bond. Okay, and now we need to talk about the chemical properties of H2O2. And the first one it is a decomposition reaction. Decomposition. Chemical properties. Decomposition. Decomposition and hydrogen peroxide decomposes on heating. It is an unstable liquid. Finely divided iron, copper, gold, platinum, MnO2, and metal ions like Cu2 plus, nickel 2 plus, and traces of base act as a positive catalyst that is destabilizes for its decomposition while orthophosphoric acid C6H5NHCOCH2 that is the acetanide and glycerol ethyl alcohol act as the negative catalyst or the stabilizers for its decomposition. And now the nature, what is the nature of that H2O2? H2O2 is acidic in nature, but its aqueous solution is neutral towards litmus, and it dissociate in water to give hydronium ion. Okay, I can show that reaction H2O2 with water giving H3O plus, that is hydronium ion plus HO2. Okay, it dissociates us in to give the hydronium ion here, and the dissociation constant is 1.4 multiplied by 10 raised to minus 12 at 298 Kelvin. Now, the value of its dissociation constant suggests that its aqueous solution is more acidic than water for about Kw is equal to 10 raised to minus 14 at 298 Kelvin. The acidic nature of hydrogen peroxide is confirmed by its reaction with the alkalis and carbonates. In this reaction, corresponding peroxides are formed. I can show that it's 2O2 plus 2NaOH giving Na2O2. Na2O2. This is the peroxide and 2H2O. And also H2O2 plus barium hydroxide giving barium peroxide and water, and H2O2 with sodium carbonate Na2CO3 giving Na2O2 with carbon dioxide and water. Okay, then the formation of H2O and CO2 in the last reaction instead of the H2CO3 says that H2O2 is even stronger acid than the carbonic acid. It's H2CO3. Okay, and now the oxidizing property we need to talk about. It is an important one. The oxidizing property of H2O2. H2O2 is a strong oxidizing agent and it accepts the electron easily and itself gets reduced in alkaline as well as acidic medium like H2O2 H2O2 plus 2H plus 2H plus 2 electron giving 2H2O. Okay, and the standard electrode potential is E equal to plus 1.77 volt here, and of HO2 minus plus H2O plus 2 electron giving 3 OH minus. Here the standard electrode potential is plus 0.87 volt. Thus, in acidic medium, H2O2 is reduced into H2O, and in alkaline medium into OH minus. In both cases, oxidation number of the oxygen decreases. Here, the important point to be remember is that in alkaline solution, these reactions are generally fast. Okay, and some uh, of the oxidation reactions are the first one, lead sulfate. I think I should show all of them, some of them. Okay, lead sulfate PBS is oxidized to PbSO4. PbSO4. This reaction is like this: PbS plus 4H2O2 giving PbSO4 plus 4H2O. And so many reactions are like potassium nitrate, sodium sulfate, and sodium arsenide, hydrogen sulfide. All of them gets oxidized by the this one, and so now we are moving to the next property, that is reducing property. Reducing property. It shows both the oxidizing and reducing property. Okay, and due to electron donating property of H2O2, it also acts as a reducing agent in acidic as well as in alkaline media, and proceeds as like H2O2, H2O2 giving O2 plus 2H plus, 2H plus 2 electron, and H2O2 plus 2OH minus giving 2H2O, 2H2O plus O2 plus 2 electron. So I will show one example. For example, silver oxide. Silver oxide, that is Ag2O. Ag2O gets reduced by hydrogen peroxide. This by the reaction H2O2 giving 2Ag metallic silver with water, formation of water and oxygen. Okay, this is an example for the reducing property of H2O2. And now we are going to talk about the reaction with ozone. It's a reaction with ozone. It is a hydrogen peroxide on reaction with ozone shows the reaction like H2O2 with O3 giving H2O, water and oxygen. So with the formation of, with the reaction with ozone, we get the water and oxygen. And there is another property, that is bleaching property. Bleaching property. Hydrogen peroxide has or also exhibits bleaching property. This property is due to the nascent oxygen, which it liberates on the decomposition. It is nascent oxygen. H2O2 giving H2O plus the nascent oxygen. Nascent oxygen or nascent hydrogen are always shown in the bracket, square brackets, and the nascent oxygen combines with the coloring matter, which in turn gets oxidized. This coloring matter reacts with the nascent oxygen to give colorless matter, and it bleaches delicate materials like silk, cotton, wool, hair, feather, ivory, sound like that. And the last reaction I have taken here is an additional reactions. Hydrogen peroxide reacts with the alkenes to give respective glycols. That is alkene, like I am taking here ethane. Ethane reacts with hydrogen peroxide, giving alcohol, ethyl alcohol, and ethylene glycol, ethylene glycol. Okay, so this was the reaction, and now we need to talk about the uses of H2O2. H2O2 is germicide and antiseptic. It is used for washing cuts, wounds, teeth, ears, and so on. And it in gargles under the name perhydrol. It is 30% solution of the hydrogen peroxide. It prevents the purification of milk, liquor, and so on. Its dilute solution is used in the bleaching of cotton, wool, silk, hair, ivory, paper, pulp, and etc. And old oil paintings turn black with the time due to the formation of black lead sulfide. Hydrogen peroxide oxidizes the black lead sulfide into white lead sulfate and thus restore their color. It is used another use, and it is also used as an oxidizing agent as well as reducing agent, and it is used to produce sodium peroxoborate, that is Na2B2O2 O2 twice OH4 OH4 times. Okay, in hexahydrate state, it is used as a brightener in washing powders. Okay, and also it is used as a laboratory agent in the test of Ti4 plus, it is titanium 4 plus or chromium 3 plus or vanadium 5 plus ions. And the other usage is used as the propellant for rockets, torpedoes, and as a fuel. As a propellant, it is used to oxidize the alcohol and hydrogen peroxide to find the strength of the H2O2. H2O2. The strength of H2O2 solution may be represented by in several ways, such as gram per liter, mole per liter, normality, parts per million. Otherwise, we can find it by milligram per liter, or volume, and etc. Okay, and some important on among them are the concentration as volume and concentration as percentage, concentration as normality. Let's talk about that. And okay, first we are going to look at concentration as volume. It is equal to the volume of oxygen obtained at STP by decomposing one volume H2O2 solution. If the strength of H2O2 solution is 20 volume, and this means that 1 cubic centimeter of H2O2 solution on decomposition gives 20 cubic cube of the cubic centimeter of the O2 gas at STP, or 1 liter H2O2 solution on heating gives 20 liter O2 at STP. That's a 20 volume H2O2 solution means. What a 20 volume H2O2 solution means. Okay, and the second term is the concentration as percentage. So what is that? Concentration as percentage. Okay, and it is equal to the gram of H2O2 present in 100 milliliter of H2O2. Gram of H2O2 present in 100 milliliter. If you take 100 milliliter of H2O2 solution, how many grams of H2O2 is present in that? Okay, and thus if the strength of H2O2 solution is 8%, just say is 8%, this means that 8 gram H2O2 is present in 100 milliliter solution. 8 gram is present in 100 milliliter of the H2O2 solution. This solution not full of H2O2. Okay, and the third one, it is concentration as normality. Okay, what is that? The strength of H2O2 as normality is calculated with the help of equivalent weight of H2O2. Equivalent weight of H2O2 is 17. Okay, and what was he talking? Strength of H2O2 as the normality. Okay, as the normality is calculated with the help of equivalent weight of H2O2. Equivalent weight of H2O2 is 17, and it can be calculated by the equation normality of H2O2. Normality of H2O2 solution. H2O2 solution will be equal to strength of H2O2 solution in gram per liter divided by equivalent weight of H2O2. Okay, strength of H2O2 solution in gram per liter divided by equivalent weight of H2O2. This is the way to calculate the normality of H2O2 solution. Okay, and now we need to know the conversion of one concentration term into the another. Okay, conversion of the one concentration term into the another. So conversion. The concentration of H2O2 is expressed in terms of volume of O2. That is, we know that 10 volume H2O2 means that 1 milliliter of H2O2 at NTP gives 10 milliliter of O2 gas. These values can be changed into the other concentration terms like density, gram per liter, normality, and molarity, as that is equation 2H2O. 2H2O2 is decomposed to 2H2O and 1O2. That means if we calculate the GMM here, 2H2O2 will be having 68 gram. That is 2 multiplied by 34, 68 gram. That is 68 gram of H2O2 when decomposed gives 1 mole of H2, 1 mole of oxygen. 1 mole of oxygen means at STP or at NTP it will have 22.4 liter or 22,400 milliliter. Okay, milliliter at NTP. And from this we can calculate for the 1 milliliter, for the 1 gram, so okay, 1 milliliter here, look at me, look at here, 1 milliliter of O2 is got from 68 by 22,400 gram of H2O2. Okay, what is that? 1 milliliter. Here we got 22,400 milliliter from 68 gram. Then 1 milliliter of H2O2 oxygen is got from 68 divided by this 22,400 grams of H2O2. Okay, that's the conversion factor we have got now. So XML of H2O2 or XML of O2 is got from 68 divided by 22,400 multiplied by X grams of H2O2. Okay, so this amount is in 1 milliliter H2O2 by definition. Okay, so thus we can write 1 milliliter 1 milliliter of H2O2 is equal to 68 by 22,400 multiplied by X gram. Okay, this is by definition. This is like 1 milliliter is of H2O2 is equal to 68 divided by 22,400 multiplied by x gram, and density we can find it as density will be equal to, it is the gram per milliliter. Okay, density we can show it as the gram per milliliter. So 68 by 22,000, 1 milliliter contains 68 by 22,400, so that is the density also, 22,400 x gram per milliliter. And now the concentration in gram per liter, the concentration in gram per liter, in gram per liter is equal to this gram per liter, not gram per milliliter, gram per liter. That will be equal to 68,000. So 68 divided by 22,400 into x multiplied by, we need to change this milliliter to thousand. So divided by thousand, and when it comes when we takes the reciprocal, it will come upward. That is, we multiplied by thousand. Okay, that means we will get gram per liter concentration as 680x divided by 224 gram per liter. Okay, and now the normality, what was the equation for normality? The concentration in gram per liter divided by equivalent weight of the H2O2, that right? So concentration in gram per liter divided by equivalent weight, that is equation for equation for normality. So we get the gram per liter is 680 divided by 680x divided by 22.4 or 224 gram per multiplied by the equivalent weight is 17, so divided by 70, that is 1 by 70. Equivalent weight of H2O2 is 17. Okay, and now that is, we get normality as, by the calculation by division, we get x by 5.6, x by 5.6. X is the amount we take. Okay, and the molarity, now we need to find the molarity M, which will be equal to concentration in gram per liter divided by the molecular weight, that's equal to 680 x by 24 multiplied by 1 by 34. It is a molecular weight. Okay, 1 by 34. And now that is, by the calculation, we get m equal to x by 2 times that 5.6, that is 11.2. Okay, that was the conversion factors or conversion methods. Now let's look at some questions. So the volume strength of 1.6 normal H2O2 solution is, volume strength is asked to find the volume strength. Here the normality of H2O2 is given, so we can find the normal strength, that is strength equal to the normality multiplied by this normal strength, not the volume strength, normality multiplied by equivalent weight. From that we can apply, the normality is 1.6 and equivalent weight of the H2O2 is 17, so we get the answer 1.6 into 17 gram per milliliter, gram per liter. Okay, this is the strength. Now we know that 68 gram of H2O2 gives to 22,400 milliliter of H2O2 of O2. Okay, so we know that 1 gram H2O2 gives 1 gram H2O2 gives 22,400 divided by 68 gram, 68 gram of, I mean milliliter of oxygen. Okay, so we get that 1.6 multiplied by 17 gram of H2O, that is strength here in the solution, then given solution of the H2O2 will give 1.6 multiplied by 17 multiplied by 22,400 divided by 68 milliliter of O2. By the calculation we will get that it has the 8,960 milliliter. 8,900 milliliter. 8,960 milliliter. Okay, and but know that 1.6 multiplied by 17 gram of H2O2 is present in 1000 milliliter. That is the strength, right? 1 liter means 1000 milliliter. The 1000 milliliter of H2O2 solution contains 1.6 multiplied by 17 gram. So hence we can say that 100 milliliter of H2O2, 1000 milliliter of H2O2 solution will give oxygen equal to, that is 1000 milliliter of H2O2 solution. H2O2 solution will give 8,960 milliliter of O2. So 1 milliliter of H2O2 gives 8,960 divided by 1000 of O2. That means we get 8.96 milliliter of O2. So therefore 1 milliliter, and is the volume, that is the volume strength. Okay, the volume strength of 1.6 normal H2O2 is 8.96 volume. 8.96 volume. So that was the answer to the question. So option B is the right answer. So moving to the next question. So 5 milliliter of H2O2 solution liberates 0.508 gram of I2, that is iodine, from an acidified Ki solution. The strength of H2O2 solution in terms of volume strength at STP will be dash. So we need to find that. So here let the normality of H2O2 be n. Okay, then equivalence of H2O2 will be equal to 5 milliliter, right? So 5n divided by 1000, 5n divided by 1000, that gives n by 200, and equivalence of I2, we know that the this 0.508 gram, equivalence of I2 will be equal to 0.508, that divided by the mass of, or the atomic mass of the iodine, that is 127. So that will be the equivalent weight of equivalence of the I2, and now we can equate them. Equivalence of the H2O2 will be equal to the equivalence of I2, so we can equate that and find the normality of the H2O2. So that will be n by 200, that is equal to 0.508 divided by 127, and that's it. So n will be equal to 0.508 multiplied by 2200 divided by 127, and that's equal to point 8 normal H2O2. Okay, and if the volume strength, we need to find the volume strength, right? So if the volume strength is x, if volume strength equal to x, then normality, we know that the volume strength x divided by uh, 5.6, x divided by 5.6. We got that from the previous slide. I have taught that. And x by 5.6, so x will be equal to n multiplied by 5.6. X will be equal to n multiplied by 5.6, that will be equal to n. Here it is, we got that point 8 multiplied by 5.6, and that's equal to 4.48 volume. Okay, so that's the answer. And now we are moving to the so moving to the next topic, that is structure of H2O2, which is an important one. Structure of H2O2. The following two structures have been suggested for the hydrogen peroxide, that is so like this, like the bend shaped bond in the water, and a coordinate bond with the another oxygen. This model is called as the Kingsets model. Kingsets model, Kingsets formula. And another one, it is sorry another one is like this. This is Bayer's formula. Okay, these two structures are useful for the H2O2, and there are evidences for both of these structures. Evidence for Kingset structure is that H2O2 is an oxidizing agent. The reaction in H2O2 acts as an oxidant. One oxygen atom per H2O2 molecule is decreased. Thus, the structure explains the instability of one of the oxygen atom, and that's the evidence for Kingset structure. There are a lot of evidence for the Bayer structure. Like H2O2 is a weak dibasic acid, and it has two OH groups. Therefore, it has two OH groups, and therefore it forms two series of salts such as NaHO2, Na2O2, and that's an evidence. And the second evidence is ethylene glycol is formed by the action of H2O2 on ethylene. This confirms the presence of two OH groups in H2O2. Okay, and H2O2 reacts with the ethyl sulfate, and diethyl peroxide is formed, and this is one on reduction gives ethyl alcohol. From this reaction, it is concluded that O peroxo bond, that is O single bond O, is present in H2O2, and one H atom or one hydrogen atom is bonded to each atom. And X-ray study confirms the presence of peroxo bond in peroxides such as Na2O2, BaO2. Such compounds. Dipole moment of H2O2 is about 2.1 D, and this shows that all the four atoms in H2O2 are not in one plane. X-ray studies shows that the H2O2 is non-polar molecule, and H2O2 molecule may be pictured as lying on spine of a book open at an angle of 94.8 degree, and one hydrogen atom is placed on each cover. The the two oxygen atoms are present along the axis of spin of the book, and the HO bonds make an angle of 94.8. So I can show that before that the some parameters are oxygen bond length will be equal to 1.49 in that structure Armstrong. OH bond length that is equal to 0.97 Armstrong. And about the OH or OOH angle will be equal to 94.8 degree. 94.8 degree. And for H2O2 in solid phase, the dihedral angle between two planes is different, and the bond length and the length of OH bond length is different, as I can show that in the figures. Like this. Okay, here this is two oxygen bonds in the spine of a notebook, and this hydrogens are on the cover of the notebook, and like this we can draw. Now it is like a notebook. This is how it looks like, and the angle between them is approximately, this angle is 1.5 degree, and this angle is about 94.8 degree, and the bond length between oxygen and oxygen is 147.5 picometer. Here it is 95.0, that's 95 picometer. And this is of the gas phase. Gas phase will be like this, and in the solid phase there are some changes, like here this angle will be 90.2, and this here this angle will be equal to 101.9 degree, and this bond length will be 145.8, and here this bond length will be 98.8. And that was the structure of the H2O2. And now let's move for the next topic, that is hydrides. This is the open book structure. Okay, open book structure of H2O2. And now next topic, that is hydrides. The compounds of hydrogen in which hydrogen is supposed to be present as H minus. H minus H minus are called the hydrides, and the oxidation state of H in these compounds is -1. Based upon their physical and chemical properties, hydrides are of the following three types. That is, first one, it is ionic or salt like hydrates, and second, the molecular or covalent hydrates, and the third one, it is metallic or interstitial hydrates. So first one, it was ionic or salt like hydrates. Ionic or salt like hydrates. These are the compounds of hydrogen with most of the S block elements, and these are formed by the transfer of electrons from metal to hydrogen atom. These are white crystalline solids, have ionic lattices, high boiling and melting points, and behave as salts. They can conduct electricity only in fused or molten state, and their density is higher than that of the metals, and their aqueous solution are strongly alkaline. These hydrates are famous for complex formation and used as good reducing agents. And the next one, it is molecular or covalent hydrates or covalent hydrates. So what is that? These are the compounds of hydrogen with p block elements, and their bonds are mostly covalent in character. In some cases, partly covalent or partially ionic character. For example, HF in HF, and these have molecular lattice is soft in texture with a low melting point and boiling point and low electrical conductivity. Okay, and acidic character in these hydrates increases while moving left to right in a period. For example, NS3 is in base. NS3 is a base, while H2O is neutral and HF is acid. HF, this is base as this neutral. HF is acidic. pH3 is weak base, and H2S is weak acid. HCl is strong. It's like from the left to right. Okay, and the molecular hydrates are named with the suffix ane, that is phosphane. For example, phosphane, this pH3 is phos phosphane, pH3 phosphane. And oxidane. What is it? Oxidane. It is a familiar one, that is H2O. Oxidane. Acane, that is NH3, ammonia. Acane, and so on. And out of the following three types, electron deficient hydrates, electron precise hydrates, electron rich hydrates. Okay, what is it? Deficient, precise, and deficient. Precise. Second one, it is third one, precise. Oh, third one, that is rich, electron rich hydrates. Okay, so electron deficient hydrates with elements of 13th group, which normally behaves as Lewis acid. For example, B2H6, and electron precise hydrates with elements of 14th group, and for example, CH4, and electron rich hydrates with elements of 15th, 16th, and 17th groups are H2O, NS, for example, H2O, NS3, and HF, and so on. And here the excess electron is being present as lone pair. That's NS3 have one lone pair, H2O have two lone pairs, HF have three lone pairs, and the presence of oxygen, nitrogen, and fluorine results in the hydrogen bond formation. And presence of hydrogen bonds lead to high boiling points and high permittivities and aggregation in such compounds. Okay, so the next type of hydrates is metallic. Third type is metallic metallic or interstitial hydrates. These are formed by the reaction of D and F block metals with hydrogen, and these are non-stoichiometric hydrates and show electric conduction. These hydrates are generally formed by the first one, it is transition metals of group 3, 4, 5 of D block, and the second, the chromium metals of group 6, and third by the F block elements, and it may be noted that elements of groups 7, 8, 9 of D block do not form hydrates at all. This inability of metal of group 7, 8, 9 of the periodic table to form hydrates is referred to as hydrate gap of D block. Hydrate gap, that is 7, 8, 9. 7, 8, 9. Hydrate gap of D block elements. Okay. And in these compounds, hydrogen atoms are supposed to occupy interstitial position and the metal lattices. And some scientists consider these compounds as simply solid solutions of hydrogen. The composition of these hydrates may not correspond to the simple wall number ratio, and therefore they are also called non-stoichiometric hydrates, and their composition is also found to vary with the conditions of temperature and pressure. Some examples of interstitial hydrates of elements of group 3 to 5 are scandium, with scandium, that is SCH2, yttrium, which is YH2, YH3, and with lithium, LiH3, and CrH, TiH2, titanium hydride, zirconium, hafnium, vanadium hydride, niobium, NBH, tantalum, H, and so on. Okay, so to know more about the Cloudmentor, visit our website. You can Google by typing Cloudmentor Gaurish. Site appears as the first result, and or simply search Cloudmentor and you will get the site as the third result. And also you can follow us on different social media platforms, and you can follow us on Instagram, and you can follow on WhatsApp. I have created a WhatsApp group for discussions on different doubts you have, and the links are given in the description box. Also a Telegram group for discussion and the same purpose, and a channel is also formed for giving off your learning steps, and all the links are given in the description box. You can check it later. You can also ask your doubts as comments in YouTube, and if you want more videos which would be uploaded in the coming days, please subscribe our channel and press that bell icon for getting notifications on time.
Hope you guys understood the topic. Thanks for watching my video. Always be free to ask questions. Subscribe to my channel for more videos. If you like this video, share it with your friends. See you guys.